because this video is about the outlier test and finding out what outliers are. So we're pretty good at boxing whisker plots. So if I gave you a set of data, you guys know how to create a boxing whisker plot with it. Just so you know, I already put this in order, so you don't have to worry about it. And you want to find the five number system. So the 5-number system first. And the 5-number system we use in the boxing whisker plot is basically what makes it. It's the minimum value, and it's Q1, so it's the lower quartile, the median, which is Q2, then Q3, and then you find the max. 1, 2, 3, 4, 5. So that's the max. That's the last one. So it's pretty easy to find the min. You just look at the middle. You look at the smallest number in this list, and of course is 1 in this problem. So the min equals a 1. Q1, or to find that, you got to first find the median. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers in there. So if you got 11 numbers, to find the median, an easy way of finding it is taking 11 numbers divided by 2. You get 5.5, and you round it up to 6. So the 6th number is the middle number. So forget 1, 2, 3, 4, 5, 6. I know that's my median, that's my middle number. If you check it, I got 5 numbers on this side. I got 5 numbers to the left. It always works. I know some of you guys, I see you marking off the ends, and that still works. If that's how you do, you just mark off one end, and then another one, and another one, eventually find the middle. But either way, it's true. Either way, it's going to find it. That's useful if you get a really large set of data, and you don't want to actually do that, marking off each one. But anyway, so the median in this problem is the 6th number, so it's 8. So the lower quartile should be the middle of that set. So in this case, we got 5 numbers here. So the middle of it is the 3rd one. If you think about it, well, 5 divided by 2 is 2.5. You round it up, it'd be 3, right? So it gives you the 3rd number in that list. There's an arrow over here. So 3 is Q1, the lower quartile. And the 3rd number from the left here is 12. And that's going to give you the median. I'm sorry, the Q3, so that's 12. And the median we already said was 8. And the max in this case is 40. Now, looking at this set of data, the numbers for the most part are like around 10. Like it's 1, 3, 3, 4, 6, 8, 10, 10, 12, 13. You got this really huge number 40 here. And that stands out a bit because if these like salaries are any number, like the number of shots a person made in a basketball game, whatever, this all seems pretty close together. And then all of a sudden you got this one huge number just throwing everything off. So if I found my mean here, it would change my mean. It would skew my data. What I mean is, typically, data is supposed to look like this. Most of the points should be around the mean. And the mean is the average. And we call that mean X bar. This is an X with a bar on top. So that X bar, if you ever see that, the math is our symbol for mean or average. The mean should be right there in the middle of the data. And most of the data should be kind of evenly split around the mean. But when we have outliers like this, it's most of the data is in one place. But now, instead of our mean being here in the middle of the data, we got one outlier that's like either way below the mean or way above the mean. It makes our mean shift towards it. And so now the mean says this, and it says the average score is here, when it's not really a good idea what's happening because most people are around there, or whatever the thing is measuring. Or if you got one on the high end, it takes our mean from being where it should be, which is where most of them are, to being right down there. So it shifts our mean to a place that doesn't describe the data as well as it should. So we call this skewed data. So skewed. This one is skewed left because the numbers on the left side, that's the small ends on the left side, and that's what some outliers affecting our data. We call this one skewed right because you got some number on the right side that's skewing our data, and most of our data is on the left. It's kind of look like a whale's tail, and wherever the tail is pointing, that tells you where it's skewed at. But yeah, that's what that means by skewed left and skewed right, and that's what X bar means. So in this case, we have an outlier. We got some number that's skewing our data, and it's affecting our mean in such a way that we wouldn't use our mean or the average of all these numbers to describe whatever this data set is representing. It might be better to use our median because our median is closer to where all those numbers are. So in this example, our median would be a better number to choose to represent the data. And basically decide whether or not that is an outlier. There's a formula for it. Basically it goes like this. Decide whether or not that's an outlier. If I came up with my data set for this on a box and whisker plot, I know my median would be 8. I know my lower quartile would be 3. My upper quartile would be 12. And this is my box. Something like this. And we got this number that's 40 that's way out here. It's probably like right there someplace. That's the 40. And then we have the 1 that's like right there. So basically to decide whether or not it's an outlier, we do this. We find our interquartile range. Inner quartile range, IQR. We've used it before. You guys did really well on the quiz on it, so I'm pretty sure you understand what I mean by interquartile range. It's basically the box. Basically the box, right? So it's basically the box and the whisker plot. So to find an interquartile range for this set of data, we'll start, it's basically Q3 take away Q1. So we know Q3 is 12, we know Q1 is 3, that difference is 9. So our IQR is 9. It's our interquartile range. So that's from Q3 to Q1. To find out whether the data is outlier, we basically take our interquartile range and we multiply it by 1.5. We go out 50% larger than the box. Basically what that means. So we take our interquartile range, 9, and we multiply by 1.5. Multiply 9 by 1.5, and check that with a calculator. Just for the record, 9 times 1.5 is 13.5. So that means that in order for it to be an outlier, I would take Q3 and I would add 13.5 to it. And that tells me the highest numbers allowed for this data. So I'm going to take 12. I'm going to add 13.5 to it, and that is 25.5. So on the high end, this data could be no higher. No numbers are allowed higher than 25.5. This is called our upper boundary. You might call it upper limit. Depending on who wrote the textbook, you might call it upper limit, upper boundary. That means, given this data set, it would make sense to have any numbers outside of 25.5. That's as high as it can be. And then on the low end, you would take our Q1 value. You would take Q1, and we subtract 13.5 from it. So it's going to be Q1 would be 3, take away 13.5, and I think that's going to be 10.5. Make sure I'm right though. So negative 10.5. So on the low end, it could be no lower than negative 10.5. So this is our lower boundary. Lower boundary. So we can't have any numbers in this data set that's lower than negative 10.5 or higher than 25.5, or else we note that as an outlier, as in it's not true for most of the data. So this I'm going to label as an outlier. And that's it. That's how you find out whether something is an outlier. You essentially, you find your 5-number system, which is the minimum, Q1, median, Q3, and the max. Then after you find that, you find your interquartile range, find out what IQR is. This is a 9. You take the IQR and you multiply it always by 1.5. Whatever IQR times 1.5 is, you take that number, you add it to Q1, you subtract it from Q3. That tells you your upper boundary and lower boundary, any number outside those boundaries we throw out. Like there's no numbers lower than 1, so we don't have to worry about throwing out any lower numbers. But there's definitely a number that's higher than 25.5. That's what it means. That's all I have. Good luck.